I suppose, is it recording now? Yes. Okay, Dan, maybe you can do the introduction.
Yes. Well, first of all, very welcome again to the second seminar out of the Semi-Classical Online Network Exchange series. We are very happy to welcome Erik Curiel to give the seminar this month. After getting his start in studying philosophy and physics at Harvard, Erik Curiel got his PhD in philosophy of physics at the University of Chicago. And currently he has quite a list of affiliations, and they're all wonderfully displayed on the screen. So he's a member of the Lichtenberg Group for History of Philosophy of Physics in Bonn, a member of the Black Hole Initiative at Harvard, and also a member of the Quantum Information Structure of Spacetime Consortium. We're looking very much forward to your talk, Erik, so please, the floor is yours.
Thank you. And I especially want to thank Don and Eleni and Paolo and Benito and everyone else who's organized this truly wonderful online forum for people interested in semi-classical gravity, and for the honor of inviting me to give a talk today. So as Carlo already plaintively asked about the number of slides, you can see there are 67 slides. I'm not going to get through all of them. But I put a bunch more on there for the sake of completeness, so that when the slides are posted online, if people are curious, they can go look at some of the things I didn't get to discuss in the talk today to see in somewhat more detail my opinions on these matters. So no fear, I'm not going to try and get through 67 slides. So I'll begin with a quote from someone I think we all should attend to at one point or other in our lives, Francis Bacon, one of the fathers of the move towards in the empirical study of nature. In one of his aphorisms in the Novum Organum, he says, "The subtlety of nature far exceeds the subtlety of sense and intellect, so that these fine meditations and speculations and reasonings of men are a sort of insanity, only there is no one at hand to remark it." Well, I'm actually here today to remark it, so that's the plan for today is remarking it. But I'll start with a very quick apologia, Socratic apologia for those who aren't familiar with philosophers, because as Don said, I'm primarily a philosopher. I consider myself maybe 75% philosopher, 25% physicist. So just to give you a sense of what I see my job as philosopher is in regard to interacting with and discussing and analyzing physics. So semi-classical gravity and black hole thermodynamics, they are, without a doubt, the most widely accepted, most deeply trusted results in theoretical physics, in which GR and QFT and thermodynamics are to my mind, three most basic, fundamental, and successful and deeply entrenched theories, in which those three work together in seemingly fruitful harmony. And this is especially remarkable when one reflects on the fact that we have no experimental or observational evidence for any of it. And we have no hope of gaining any empirical access to the regimes in which we would expect the effects that these frameworks and theories predict anytime in the near future. Why do we trust it so much? Because we do. If you talk to almost any theoretical physicist today, whether they work in the field or not, and you ask them, do you believe in Hawking radiation? They will almost universally, almost unequivocally say, absolutely. I find this striking, really striking. So to motivate some questions about this situation, I'm going to read another quotation, this one from someone no one here, I hope, should have any doubt is someone that we all should listen to and attend to at some point in our careers. And I mean James Clerk Maxwell, whom I regard as probably the third greatest physicist of all time after Newton and Einstein, and probably philosophically the most sophisticated and deep physicist who ever lived. In his address to the mathematical and physical sections of the British Association in 1870, Maxwell said, "We are met as cultivators of mathematics and physics. In our daily work, we are led up to questions the same in kind with those of metaphysics, and we approach them, and now I want you to pay a special attention to this last part. We approach them not trusting to the native penetrating power of our own minds, but trained by a long continued adjustment of our modes of thought to the facts of external nature." Now, in a field such as BHT and semi-classical gravity, where we have not only no empirical experience or evidence to test our theorizing, but what I consider to be a much more important and much more severe problem, we have no empirical evidence to guide and constrain our theorizing, where we have exactly not been, as Maxwell demands, trained by a long continued adjustment of our modes of thought to the facts of external nature. These investigations are necessarily speculative in a way unusual even in theoretical physics. Technically sophisticated, conceptually deep physical questions, I think, are inextricable from subtle philosophical considerations spanning ontology, epistemology, methodology, and, as Maxwell remarks, metaphysics. Again, in a way unusual even in theoretical physics. In such a situation, what besides the intuitions of eminent physicists do we have to guide our theorizing? Because if we're honest with ourselves and we look at the literature, when we look at how, for lack of a better word, fads in this area come and go, and particular questions and issues all of a sudden gain extraordinary prominence, it is almost always because some very eminent physicist has declared it so. Can we have in this situation any epistemic control over the situation at all? And this, I think, is the fundamental question that we have to face when we think about the foundations of black hole thermodynamics and semi-classical gravity and problems such as the information loss paradox that almost everyone, most people in the field think of as a truly deep, important problem, urgent problem that must be addressed and one hopes solved. Now, what I mean by epistemic control, actually, I mean quite a lot by that phrase, by that term. I probably will not be able to get to the slides in which I discuss it. They're at the end of the slides. So if you're curious about what I mean by that and why I think in fact we don't really have epistemic control over these frameworks and these theories, I invite you to look at those slides later when they're made available, since I am pretty sure I won't be able to get to them in this talk. In such a field, in this field of black hole thermodynamics and semi-classical gravity, I actually see no clear line to be drawn to demarcate physics from philosophy. And so my task here today, as this Socratic apologia suggests, is to play Socratic gadfly, which, recall, if you are familiar with the Platonic dialogues, which Socrates does his thing, involves a lot of clarificatory exposition of what the fundamental issue is. And that is what I'm going to start the talk proper, the discussion of DHT and info loss in a moment by doing. And it's also good to recall the charge that got Socrates executed, which was corrupting the youth. And I hope to do that here as well. So the outline for the talk, I'm going to discuss what is commonly meant by information loss when it's discussed. And I will, as will quickly become clear, there is in fact not one single problem that people mean or one single issue or when they talk about information loss in this area. There aren't even two. Some people may think, there's the standard problem and the page time and the page curve problem. There are actually many. And I'm going to first try to disentangle them and then discuss what it is, why they seem problematic, and what possible attitudes and responses to them have been and are. One of the most popular, at least one of the most widespread, if not popular, responses to the information loss problem, if in fact we can give it the honorific of the definite article, is freaking out. You know, a lot of people really freak out about it. And I'm gonna see if I can unpack why it is that people seem to freak out and whether this freaking out is justified. And then I hope to get to some discussion of the ways in which I think one can and perhaps ought to view semi-classical gravity as just an effective field theory, and why that will mitigate, I think, some of the urgency of the of information loss. And the last slides, which, as I say, probably won't get to, are laying out and discussing the idea of epistemic control and why I think it's of particular urgency in this area, the lack of it, which I think we in fact do lack. So information loss is said in many ways. So in a nutshell, I'm assuming everyone here more or less knows the basics of black hole thermodynamics, more or less knows what semi-classical gravity is. So I'm not going to give any elementary discussion of that. But I will just very quickly give an outline of what the heart of the problem seems to be. So stuff collapses to a black hole or is thrown into an existing black hole. The O'Hare theorems tell us, you know, at least when the black hole has settled back down to stationarity or settled down to stationarity in the first place, that at the classical level, all information about that stuff is utterly effaced from the outside, because the black hole from the outside is characterized by at most three macro numbers: mass, angular momentum, and electric charge. When quantum effects are taken into account, the black holes emit Hawking radiation, far away, ignoring gray body factors. The radiation has an essentially Planckian spectrum. It carries positive mass energy away, so the black hole shrinks or evaporates. I'm just telling the standard story. I actually have several problems with almost every step I've mentioned so far, but it would take us too far afield to go into all of that. Eventually, the black hole completely evaporates, or depending on how you think about these things, at least the issue is that it gets small enough that it doesn't have enough mass energy, enough microstates, what have you, to maintain a record of everything that collapsed or fell in. And so that's a way of trying to shield us from the issue of presumably quantum gravity effects that take over, that we don't have yet a deep understanding of, near complete evaporation. But Plancking radiation carries no information except for an encoded temperature. It's in a sense one can make precise, as random as a physical system can be. So all information about what collapsed or fell in is irretrievably lost. And this seems to be a violation of a fundamental principle of quantum mechanics, in particular unitary evolution. And that is the heart of the paradox. Now, to try to make things a little more precise, I'm going to introduce briefly two notions of dynamical evolution that seem to be relevant here. The first is the notion entirely within classical general relativity and classical matter fields. It's mathematically well-defined, it's physically well understood. You impose initial data on a slice, on an achronal slice, initial data being the Riemannian metric on the slice, and the conjugate momentum, which is essentially just the extrinsic curvature. And then you evolve that data into the domain of dependence of that slice, governed by the Cauchy development induced by the Einstein field equation. Well understood, under control. A second notion of evolution that seems to be relevant here is a notion that we would like to have for quantum field theory on curved space-time. And this is, I say it's aspirational because we don't yet have a good, a well-defined representation of this, understanding of this either. So initial data presumably will be something like the quantum state defined on a Cauchy slice. and I'm restricting, now I'm being a little more restrictive. I'm demanding not just a slice, but a Cauchy slice, because it seems as though for these issues, we really do want to work in a globally hyperbolic spacetime. And then evolution between, Cauchy surfaces will be governed by something like a Schrodinger unitary evolution. But, as I say, it's aspirational because we really don't know how to do this on curved spacetime in any rigorous, truly satisfactory way. Now, given this, that there are...
Erik, just to understand, you wouldn't consider standard QFT on curved spacetime like Birrell and Davis more than aspirational?
Well, I mean, Burrell and Davis does almost always path. They use the path integral formalism, if I remember correctly, and the path integral formulation is very powerful, but it's not the kind of evolution that I'm talking about here. The path integral doesn't give you, a true unitary flow between Cauchy surfaces.
Okay, let's not go into, okay.
So one might have thought the central issue of the information loss paradox would be posed as something like, are these two notions of evolution in an appropriate sense consistent? In fact, it's never posed that way, in large part because no one knows how to combine a 3+1 Einstein field equation with anything like the Schrodinger equation, whether it's an appropriate combination or not. And you might think, well, we have a semi-classical Einstein field equation. Surely that will help us out here. But it won't do the job because the semi-classical Einstein field equation deals only with the expectation value of the stress energy operator, not with the state of the quantum field, which is what we really want to know. Rather, in the context of evaporating black hole spacetimes, there are at least 5 questions that are commonly posed, sometimes only implicitly. None are always clearly distinguished from the others. In fact, I would say they're almost never clearly distinguished from the others. None are clearly equivalent to or even clearly related to the others, although some prima facie have more intimately entangled than others are, as we'll see. Those 5 are, these are not, the names I've given them are not standard in literature. They're just simple names I came up with just for ease of reference. So there's what I call the Hawking problem. Is there a unitary scattering matrix from scri minus to scri plus? The final state problem is Hawking radiation, in particular, say the quantum state of the field on some slice, preferably a Cauchy slice, in a pure state after evaporation ends. There's the recovery problem. Can the information encoded in a physical system be recovered after it enters a black hole, whether that system was part of the initial collapse or thrown in later? There's the causal structure problem. What is the global causal structure of a space-time with an evaporating black hole? And is it compatible with unitary evolution? And there's the page curve problem. Does the entropy of Hawking radiation decrease at late times during evaporation? Now, they do really all have more or less vaguely to do with the idea of unitarity. And unfortunately, when people discuss this, they're not always clear what they mean by unitarity, and it really is not a univocal concept, I'm sorry to say. Unitarity in this context, the idea of unitarity is often glossed quite differently. For instance, it's glossed as the possibility of retaining or maintaining determinism or predictability or conservation of probability or evolution of pure states into pure states or entanglement between in and out modes of Hawking radiation. And those are the most widely used ones, but there are others. Sometimes people talk about complexity, and there are many, many things that people seem to mean when they talk about unitarity in this context. And it's all, of course, exacerbated by the fact that even in the standard orthodox scattering theory, unitarity actually is used in at least 2 different ways, meaning either conservation of probability or evolution of pure states into pure states. I mean, of course, there's also the sense of unitarity that the mathematical physicists will immediately think of, as a property of a self-adjoint operator on a Hilbert space. And that is, of course, that is intimately related to many of these notions as well. But it's not always clear exactly how all these notions relate to each other. And so it's also not always clear which notion is at play in any of the 5 questions that I claim are the ones most commonly asked in this context. So there's a lot to disentangle here when one really wants to ask what is the information loss paradox. But we can at least at this point now perhaps frame the question as, can quantum fields unitarily evolve in a space-time with an evaporating black hole in any of these senses of unitarity? Now, this is all complicated by the fact that there are many, really many, and for the most part, really radically different forms of derivation of the Hawking effect. So, I mean, if you want to derive the Hawking effect, you have a lot of choices to make. You first have to make some choices about the space-time and the space-time structure you're going to be working in. You might characterize your shape, the shape and character of space-time either by choosing an exact solution or by an abstract characterization by just specifying, say, the type of horizon, the topology, the symmetries, the asymptotic structure you'll be dealing with. You have to decide on the region of analysis. Is it going to be a local or global region? Is it going to be near horizon or asymptotic? You almost always want some form of cosmic censorship. You almost always want some causality conditions, some stability assumptions about the horizon, although those are almost always implicit. And there are many other choices about space-time you have to make. Then you have to make matter choices. What formulation of QFT are you going to choose? Because there's a lot to choose from already in this game. S-matrix, algebraic, canonical based on Lagrangian, covariant phase space, low energy perturbative quantum gravity, and on and on. You have to choose the flavor of your QFT. It's almost always scalar and bosonic. It's just that simple. But some people get ambitious and try and derive the Hawking effect for more physically complex flavors of field. You very often, even if only implicitly, impose some average energy conditions or quantum energy inequalities. You have to choose. You may want to choose a particular state. If so, which, or you're just going to impose generic conditions on it. If you choose a state, you may need to choose an eigenbasis. You always need some boundary conditions. You always need some kind of approximation because the full theory is just too difficult to work with. You might assume that the stress energy tensor operator is constructible because you don't always have a proof of that. In which case you might need, say, to impose niceness of state conditions, e.g. the state is Hadamard, or some adiabaticity. I can never say that. Adiabaticity conditions, and on. And then there are joint space-time matter choices to include back reaction. Almost no one ever does that. 99.9% of derivations of Hawking radiation are just quantum field theory and curved space-time, no coupling of the quantum field to the space-time curvature at all. Although, of course, there is still some interaction between the quantum field and the space-time, because the evolution of the quantum field is presumably guided by the affine structure of the space-time. Otherwise, you don't even know how to solve, how to get any evolution off the ground in the first place. You have to decide what kind of regime you're working in: stationary, quasi-static, quasi-steady, or dynamic for the matter plus the space-time. You may want to impose some entropy conditions like the GSL. And now when you put all this together and you try and figure out how many different possible derivations there are of the Hawking effect, I actually just did this as a fun exercise. You just work through all the possible combinations, trying to make sure you're not including any that are, mutually inconsistent, and just a simple combinatorial calculation. I came up with 2,069,547,534 possible derivations. Now, I have not examined all 2 billion of those in the literature. To be fair, there are probably only a couple hundred in literature of forms of it. There are thousands and thousands of papers that give a derivation. Why is this relevant? You might think, well, who cares? I mean, Curiel, this is kind of silly. Why count the number of possible derivations in this way when, the same thing arises in, all of physics. You want to solve a problem, you have to make a lot of choices, set things up, and you don't worry about how many possible ways there are of doing it. Why is this relevant? Well, it's relevant. Oh, there's actually one more slide to tell you. I want to show before I tell you why it's relevant. So I have, in fact, done a lot of looking through the literature and I'm on this issue, and as stultifying as it can be, I can tell you what the most popular forms of derivation are, in fact. S matrix a la Hawking's original, pass boundary a la Unruh's original, algebraic, various ways of canonical, tunneling, anomaly canceling, more general stress energy tensor analysis, near horizon symmetries, thermal atmosphere, holographic, and on. And by popular, I actually have a criterion for popular, which is there had to be at least 3 different independent people or groups who published at least one paper in which they make this kind of derivation, and that paper has to have at least 10 non-self citations. And even using that criterion, somewhat arbitrary, but I think at least somewhat revealing, there are at least this many that are popular in the literature. Now, why is this relevant? Well, I think it actually leaves us 2 very serious problems to consider. One, in fact, if you look closely, this really is not a case of how things are in most of physics, because a lot of these frameworks and a lot of the choices you have to make really are either mutually inconsistent with each other, or they are not in any way clearly, we don't understand them well enough, either to show how they actually are related to each other, how to translate ideas and arguments and results from one to the other. We don't even understand them well enough to know whether or not they are related in such a satisfactory way. So first serious problem, how do all the radically different possible derivations square with each other, if they do at all? Second serious problem, would an answer if the information loss paradox formulated with respect to one hold for any of the others? And this actually becomes these 2 problems I think are especially serious in light of a third problem, which is that why these are serious problems in the first place is because when you go in detail through many of these different types of derivations, they actually suggest radically different physical interpretations, different physical pictures of what the Hawking effect is. They suggest radically different physics. Just as an example, let's look at whether or not derivations provide us with a way to talk about a space-time picture of dynamics. So on the S matrix type of derivations, the iconal approximation, almost always used, gives a well-defined dynamics formulated using space-time geodesics, almost always null geodesics, because it's almost always massless scalar fields people use. And you get a relatively well-defined particle flux at scribe plus because of the asymptotic symmetries that are almost always assumed there. So you really do have a well-defined picture of a space-time dynamics for the radiation. Tunneling, positive energy particle tunneling out of the black hole interior, that cannot be given a cogent interpretation based on propagation guided by classical space-time geometry without calling into question the classical space-time causal structure in the first place that the framework of semi-classical gravity is predicated on. Recall, semi-classical gravity is classical space-time geometry, quantum field propagating on it, and if you really are doing full semi-classical, then you couple the space-time geometry to the quantum field by way of the semi-classical Einstein field equation. Algebraic gives a well-defined state, but it never gives you a picture of particle production that's whether it's consistent with either of the 2 or not. It's just not clear to me actually whether on the algebraic picture we can talk about a cogent and consistent space-time dynamics for the radiation. So what is the physical content of the Hawking effect? And does it even deserve the honorific of the definite article? Is there one Hawking effect? Or, should we trust some derivations and not others to get the physics right? I don't think we know enough to say for sure, but I think this is actually a very urgent problem. We really need to understand what the relationships are between all these different derivations and why they seem prima facie to give us very different pictures of the physics. And I'll mention one final problem because I think it's also equally as urgent and bears on everything that I'm going to be talking about here. And it's one that is oddly not discussed in the literature. So the entire edifice of black hole thermodynamics, including outhouses like the information loss paradox, depend on interpreting black holes as true thermodynamical systems. And the best argument for that is Hawking radiation. Recall, Bekenstein already in '72 had proposed that black holes have an entropy and satisfy something like a generalized second law. No one believed him because they thought that, well, if black holes really have an entropy, then they should have a temperature. If they have a temperature, they should radiate. They don't radiate, so they can't be true thermodynamical systems. Hawking's calculation changed all that. When Hawking produced his calculation, within a year, almost everyone accepted, wow, black holes really are thermodynamical systems. And that really should be mind-blowing. I mean, if your mind is not blown by that, you are not thinking about this serious enough and hard enough. You're not really understanding what's going on. Saying that an otherwise undistinguished region of empty space-time has a temperature and an entropy, physical temperature, physical entropy, just like this glass of water, that should blow your mind. But unlike the incandescence of a glowing lump of hot iron, real black body radiation, Hawking radiation in the semi-classical picture is not generated by microdegrees of freedom of the event horizon, or by any microdegrees of freedom of anything having to do with gravity. Because recall, gravity is just treated as a simple classical geometrical structure. The black hole is rather not gravity. Back reaction is essentially never included. And even then, when people try to include back reaction, it's never the full semi-classical Einstein field equation. And even if it were the full semi-classical Einstein field equation, that still doesn't include microdegrees of freedom of the horizon. I mean, and remember, the reason why we think that the radiation coming off a glowing lump of hot iron is black body radiation, why it encodes a physical temperature of the iron, is because it's generated by the wiggling and jiggling of primarily the electrons, around the iron atoms. But the wiggling and jiggling of the electrons and the iron atoms themselves just is the physical temperature. I mean, that encodes the physical temperature, of the iron. That's what physical temperature of matter is. Essentially the variance in the kinetic energy of the constituent molecules. So that's indirectly. So the radiation is produced in a way that the physical temperature of the body is directly encoded in the power spectrum of the produced radiation. That is not what is happening here. They've been lying to you. Hawking radiation is not black body radiation. Otherwise, I mean, again, the fact that almost all derivations of the Hawking effect don't include any coupling of the curvature of the geometry, the affine structure, to the quantum field should already have led you to suspect that. So why should we believe, in fact, that the Planckian temperature of Hawking radiation is the temperature of the black hole when it is not generated by microdegrees of freedom of the event horizon, when our derivations don't show us that what we want to think of as the physical temperature of the event horizon, wiggling and jiggling of microdegrees of freedom, aren't what is manifestly generating the radiation. So we need further assumptions to bring these two prima facie disparate phenomena. On the one hand, the presumed microdynamics of the horizon, and on the other, those of the external quantum field, into some kind of explicit and harmonious relationship with each other, the way that the wiggling and jiggling of the electrons in the iron and the photons produced in the black body radiation coming off the iron stand in regard to each other with. Only then can we conclude that the temperature of the quantum radiation with Planckian spectrum, the Hawking radiation, is in fact a sound proxy for the temperature of the black hole itself, as determined by the dynamics of presumably its very own microdegrees of freedom. But it's exactly the lack of these bridging principles, as we will see, that calls into question, to my mind, the importance of the information loss problem. So perhaps derivations of Hawking radiation themselves, which don't depend on coupling the quantum field with the classical geometry, are already trying to tell us not to take any of this terribly seriously with regard to fundamental issues. I mean, after all, we have no evidence that anything like, perturbative low energy quantum gravity degrees of freedom, which presumably is what these micro degrees of freedom of the horizon will be, if we are able to articulate such a picture that is satisfactory. We have no evidence that anything like that couples in the right way with degrees of freedom of ordinary matter, quantum fields, photons, excited modes of massive scalar fields. Because that should be happening, for the Hawking effect to work, that coupling needs to happen at energy and gravity scales we can already probe. Because remember, the Hawking effect doesn't say I'm not going to happen for big black holes, with very, very low surface gravity, where the curvature is as small as one likes. The Hawking effect is supposed to happen no matter how low energy, well, the gravity is. And that last issue, by the way, is, as we'll see, is particularly severe for the page curve problem, which assumes that these quantum gravitational statistical mechanical degrees of freedom of the black hole directly couple the Hawking radiation in such a way that entanglement can be transferred. And again, there's just no evidence for that. There's never any mechanism suggested that for how this is supposed to happen. There's no evidence that this does happen. There are a lot of problems here. So I think our plaintiff question is now sharpened for what we might mean by the information loss paradox. Can quantum fields unitarily evolve in a space-time with an evaporating black hole in any of the senses of unitarity with respect to at least the most popular, influential, physically perspicuous, mathematically rigorous, sexy, groovy, whatever derivations you like, so that conclusions are insensitive to the temperature decoupling problem in a way that addresses at least some of the 5 formulations of the information loss paradox that I mentioned earlier in the talk. And now the shrugging and the freaking out begin. In the face of this, when presented with this problem, physicists and philosophers really do have one of 2 reactions. Either they shrug, okay, fine, unitarity may be lost at semi-classical level, who cares? In fact, that's what we should have expected for various reasons having to do with our knowledge of general relativity, what we expect the structure of evaporating black hole spacetimes to be, and how Cauchy evolution works in such spacetimes. That's generally what physicists will say if they have a background, if their intellectual genealogy and their training and rearing were in classical relativity, as mine was. If a physicist has a background in high energy particle physics and quantum field theory, they tend to really freak out. And like, oh my God, we cannot possibly lose unitarity. Are you insane? We can't do physics without unitarity. Unitarity is what they say. Well, since all these issues come out with peculiar clarity in the traditional argument about the Hawking problem, and its close, kissing cousins, the final state and the causal structure problem. So let's focus for the moment on the final state problem to get a feel for why the shrugging and why the freaking out. So this is a diagram I cribbed from Wald's wonderful 1994 book, Quantum Field Theory and Curved Spacetime and Black Hole Thermodynamics. So can y'all see this little red dot that I'm waving around? The pointer? Yes?
Yeah, we
No?
can see it.
Okay, good, thank you. I'm not just talking into a vacuum. How great. There are people there. Okay. So the setup, I hope all of you are basically familiar with, is so we have some matter collapsing to form a black hole, an event horizon. The event horizon, Hawking radiation is given off. Let's just say we're dealing with a massive scalar field or something like that. So everything's traveling on null geodesics. We're doing an S matrix we're doing something like the original Hawking calculation, and the excited modes are traveling along null geodesics, going out, propagating out to Scri+. So they're carrying positive energy away. And so the black hole loses mass and shrinks. And so, yeah, just to make sure everyone is on the same page here. So this is a Penrose diagram, a conformal, or Penrose-Carter diagram, a conformal diagram. So even though it's wonderful at showing causal structure, it is terrible at representing things, parts of the metrical structure that depend, say, on the volume element. So it looks like the black hole is getting bigger and bigger here, but in fact, it's really shrinking and going to zero volume here. And there's the standard Schwarzschild singularity forms here, and then something crazy, ineffable, we know not what happens right here. I'll just call it the evaporation point. So this is sigma 1. Let's look at we think that the quantum field we assert is when constrained to sigma 1, the state of the quantum field is in a pure state. It's evolving forward. Part of the slice is behind the event horizon. Part of it's out here in the domain of outer communication. It evolves forward. We're not going to worry too much about what we mean by that right now, but it evolves forward in some way so far up to here so as to maintain its pure state. So it's evolving in some sense unitarily. But because of the pathology of the causal structure of the space-time is not globally hyperbolic. This is not a Cauchy slice, because in particular, this sigma 2 up here is not a Cauchy slice. If we restricted the space-time, if we continued this null line of the event horizon out to Scri plus, and we restricted space-time to everything below that, then in fact, this would be a Cauchy slice for that space-time. But since we think the space-time continues on above that line, this cannot be a Cauchy slice, because this doesn't determine what comes out of the singularity, so to speak, what comes out of the evaporation point. Any crazy old stuff, for all we know, might come out. And this also cannot be a Cauchy slice, because even though it is a Cauchy slice for, if again, you restrict the space-time to this region, that is a Cauchy slice for that. But it doesn't tell you what's inside the black hole. That's not recorded here. So it looks like what's happened is the state on this part of this slice has evolved forward to this new slice, but this new slice can contain information that was only outside the horizon. So it looks like whatever information was inside the horizon has been traced out, and we are now left with a mixed state at sigma 2. So a pure state has evolved to a mixed state. Problem. So this is just a summary of what I said. I won't go through it, but since I talked through it, essentially. I will just say that, just emphasize, the root of the conflict between the quantum evolution and the Cauchy evolution is that really seems to lie in the pathology of the causal structure of the space-time. That all we have are slices, partial Cauchy surfaces, and because of that, we have what looks like what was a pure state earlier is forced to evolve to a mixed state later. So information seems to be lost. So that's the basic argument. The argument, it seems to me, just on its face, to be a very strong argument in favor of lossy unitarity in basically all the senses that one wants, that one might care about. And so one might really ask, given what I've said so far, why all the fuss about lossy unitarity in the case of black hole evaporation, but not, for instance, in standard treatments of quantum fields and effective field theory formalism, where unitarity is violated all the time. And for that matter, in the case of measurements in standard quantum theory. Because recall, in effective field theories, as used both in condensed matter physics and in particle physics, speaking very crudely, what you do is you're confident that, let's say, the high energy, the UV physics doesn't matter for the regime you're interested in, so you just integrate out all the high energy degrees of freedom. Let's say you encode them into some coupling constants, and your theory then just effectively ignores that part of the state space that you integrated out. But of course, if you're experimenting on a system or theoretically modeling a system and the dynamics start to, so to speak, want to take the system to start to try and probe that region you integrated out, then you lose unitarity. Everyone knows this, no one freaks out, it's well understood. And one might wonder why the same attitude is not taken here. Before I get to that, I just want to mention that those who freak out have propounded really a double legion of mechanisms, principles, frameworks, and arguments based on them to save unitarity. Complementarity, black hole remnants, fuzzballs, holographic arguments, firewalls, manifold varieties of ADS CFT stuff, island calculations, quantum error correction codes, final information blast, this really pervasive, promiscuously orgiastic non-locality. And remember, this is all done for the purpose of saving unitarity, for saving the fundamental principles of quantum field theory. In most cases, if you really look at what these constructions and arguments entail, they actually end up destroying the village, quantum field theory, to save the village. Most of you are probably too young. Well, I'm actually too young to remember the Vietnam War, but I'm old enough to remember discussion about it. And there was a famous incident, the Battle of Ben Tre, where an unnamed major, where the Americans just, even by the standards of the war, they just egregiously destroyed the shit out of the entire area. And when asked about it, an unnamed American major said to a journalist, it became necessary to destroy the village to save it. And I really feel that that is what's happening with a lot of the work on the information loss paradox. So this all leaves us with a poignant question, yet another one. Why do many physicists feel confident that an effect predicted by what to my mind is manifestly an effective field theory calculation? Semi-classical gravity is an effective field theory in some sense. In what sense is not clear. In particular, the evaporation due to emission of Hawking radiation. Why do they feel confident that this can be trusted to reveal features of an underlying fundamental theory of quantum gravity? So Don Marolf there's a wonderful review he wrote in 2017, where I think he lays out about as strong a case as you can make for why you should freak out. And in particular, why, and freaking out assumes that what happens at semi-classical scale with the Hawking effect should tell us something about an underlying fundamental theory of quantum gravity. But again, even though Don makes, I think, as strong a case as you can make, I still find it very unsatisfying because we don't try to glean these kinds of insights from any standard effective field theory as used, in high energy particle physics or condensed matter physics. So this is what I call the cascade problem. Why assume the failure of unitarity at the semi-classical level automatically cascades down to a failure of unitarity or something else equally distasteful at the level of a more fundamental theory of quantum gravity? So I have a few more slides, and then I will stop and take questions since I'm almost out of time. So one plausible answer, I think, for why to freak out is that in black hole evaporation, there's an articulated dynamical physical mechanism that seems directly to yield violation of unitarity, in clear opposition to standard effective field theory calculations and in clear opposition to measurement collapse and the measurement problem. Violation of unitarity is manifestly an artifact of the approximations. In standard EFT calculations, violation of unitarity is manifestly an artifact of the approximations and idealizations involved in the mathematical construction of the EFT. It doesn't reflect or represent anything physical. But in the black hole case, you can put your finger on what the mechanism is. It's this causal pathology of the space-time that seems to play the crucial role. And it happens at arbitrarily low energy, large black holes, where one expects the high energy quantum gravitational modes one ignores in semi-classical gravity, whatever they may be, to be essentially non-existent. And as I said, any possible failure of unitarity seems to follow from the geometry of classical space-time background, not the dynamics of the quantum field itself. In particular, global features of the large-scale structure of space-time responsible for the failure of unitarity. And one can, I think, very plausibly expect, insofar as one can plausibly expect anything in this in this area, that such global features will be insensitive to any quantum gravity effects near the evaporation region, since in fact those effects are appropriately localized in a small space-time region, as a recent theorem of Martin Lasord's makes precise. So Martin has this very beautiful theorem which shows that under incredibly weak and very, I think, physically reasonable assumptions, which really just try to capture the idea that there's something like an event horizon that exists for only a finite amount of retarded time, then the space-time is necessarily causally discontinuous, which is actually a stronger statement than that it's just not globally hyperbolic. And he makes no assumptions at all about what happens near the evaporation region. His theorem and conclusion hold if so long as one can, in effect, find some region, some four-dimensional region around evaporation in which you expect the classical geometry to still be a good representation. Just draw a big shell around that region, segregate it from the rest of space-time. Doesn't matter what happens in there. The result is completely insensitive to what happens inside that region. So the only way out of this, it seems to me, is in fact to invoke some kind of truly mind-boggling or derive some kind of truly mind-boggling non-locality in quantum gravity. And that's exactly what a lot of the arguments trying to save unitarity, in fact, end up doing. But the onset of new physics here, as one expects from a breakdown of EFT, when EFTs break down, so they're said to herald the onset of new physics, whether that new physics is understood or not. It's heralded by the complexity and the causal structure of space-time, possibly underwritten by extreme non-locality in the quantum gravity regime. By high entropy, that's what we expect. That's what we expect from gravitational entropy. This complexity and the causal structure that's associated with evaporating black hole space-time gives rise to a high gravitational entropy, not high energy momentum of gravitational phenomena, as for loss of unitarity in pedestrian EFTs and particle physics or condensed matter physics. So it seems to me that attempting to draw lessons about an underlying quantum gravity theory from our understanding of semi-classical gravity as an effective field theory is parlous at best, because insofar as its structure as an effective field theory seems radically different from EFTs we know and love in particle physics and condensed matter physics. So I will stop there. Thank you.
Thank you, Erik.
Thank you, Erik. That was a great talk. We had a question in the chat.
Oh, crap. I didn't see it. I was looking at my slides.
It's all right. It was early before you finished, so I thought I should wait. Should I read it, or can you see it?
So the question is, I'm in a crowded area, so I want your audio video. Oh, that's not part of the question. But doesn't the fact that a thermometer, so an Unruh DeWitt detector, coupled to the quantum field responds thermally with a temperature corresponding to the Hawking temperature, conflict with the no evidence that the temperature is a real temperature claim, i.e. the temperature decoupling argument? No, I don't think so at all, because again, several things to say about that. One, Unruh DeWitt detector measures the temperature of the quantum field, not the temperature of the Rindler horizon. You might think, well, the temperature of the quantum field is somehow dictated by the geometry of the Rindler horizon. Well, then you face the same problem. In the Unruh effect, you treat the Rindler horizon classically. There are no microdegrees of freedom, so there's no reason to think that whatever temperature is encoded, whatever temperature the Unruh DeWitt detector is detecting locally, encoded in the quantum field, in the excited modes of the quantum field, were generated by wiggling and jiggling of micro constituents of the Rindler horizon, which is what you really want in order for one to be able to say that the radiation temperature is a proxy for the physical temperature of the Rindler horizon. There's actually a lot more to say about that, but I'll keep my answer short just because I know it looks like there are other questions. Should Don or Eleni or Paolo or Benito moderate?
Yeah,
or?
we had a question by Carlo Rovelli, and then there was another question in the chat.
Hi, thanks, Eleni. Thanks, Curiel. Can you hear me?
Mhm.
Yeah. Let me put it this way. You made a lot of very good points, but I have two things which confuses me in what you say. They're related, but they're very different. And somehow I hate to defend my adversary in physics, but I think I should. So 2 points, and then please keep these 2 points separate.
Mhm.
There's something I don't think I'm with you. You seem to be saying there's a prediction, which is the Hawking radiation. It leads to a black hole information paradox. And that's, in my opinion, is profoundly wrong, because in the first slide you have a number of points which are not just the Hawking radiation. There are other additional points, which is not the Hawking radiation. And if you take a Hawking calculation, it gives a prediction. It's true that there are, what you said, a few billions derivation, but they are consistent in the region and for the prediction of what is the actual Hawking radiation, which has nothing to do with what happened on the horizon in the far distant future. It's just a specific phenomenon, which is predicted by all sorts of different things. That doesn't imply an information loss or a puzzle, which is simply the fact that a certain distance from a black hole that has formed and has remained there for a long time, one would see emission of radiation, which is not surprising at all. It would be completely shocking if it wasn't, because when you have a field and some force that acted, there's particle production. So there's nothing mysterious in particle production. It's something that would be shocking if it's not there. And Hawking did a nice calculation that, as far as we know, if you wait well enough and it's sufficiently static on this time scale, the shape, the energy shape of this emission approaches Planckian. I don't think this can be questioned, and I think you questioning it, it's correct, because that's extraordinary. Sorry, now I might be wrong, of course, because as you correctly say, we're extrapolating, but we're extrapolating in a regime in which we have no reason for extrapolate. Now. That's my first point. So I don't think it's your rhetorical thing, oh, we don't understand the Hawking radiation, is correct, in my opinion. Now, the second point is that if we go beyond the approximation that Stephen Hawking, in his very first calculation, in its Nature article, made very clear, saying this is an approximation. I have no idea what happened at the end of the evaporation, etc., etc. If we add some hypotheses, for instance, we add the hypothesis of the diagram, the Penrose diagram that you, so we had the hypothesis that at the end of the evaporation, there is this explosion that Hawking talks about, and then bingo, there is nothing. True, we get rather obviously, as Bill Unruh and Bob Wald pointed out, unitary violation, and then would be strange at all if this was the case. Now, what makes the people freak out is not that, is that independently of what happens at the end of the evaporation, much earlier than that, there is another problem. So the problem is not at the assuming what happened at the end of evaporation. The problem is before page time. Okay, so the reason people freak out in the community you're referring to has nothing to do with the end of evaporation. They know that. When they read the paper by Bob Wald, they say, of course, that's obvious. They're not surprised by that. They say, but look, before that, much before that, when the black hole is still blah, blah, there is a page argument. And the page argument shows that irrespective of what happened later, so much before the two Cauchy slices, when you still have to really Cauchy surfaces, sigma 1, sigma 2 are both already have a problem, okay? But that problem depends on something which is not the Hawking radiation, is the counting, the assumption of the counting of the number of degrees of freedom inside the black hole. So that's the extra question that comes in. So my objections to what you say are two. First, no, I mean, we have no reason to to question, no reason among the ones you mentioned that I see to question the Hawking calculation. We have a reason to question some interpretation of it, if you want, some way of dealing with it, some way of extending it. And the second, that I think you're misreading the particle physicists when you say, oh, they don't see Bob Wald point. They see it perfectly well, but they have an holographic hypothesis, which is the one implicit in page calculation. And this holographic hypothesis says that the black hole is smaller, not Planck yet, it's smaller than, say, half of what it was at the beginning. There are no enough stated size. And that's an extra hypothesis and is not the Hawking. I don't know if I made it clear, these 2 points.
That was very clear. Thank you. Those are both great. And I'm very glad you asked both because they give me a chance to clarify some of the things I said. So on the first issue, I think in fact I agree with you, and some of my rhetoric may have suggested otherwise. But so just very quickly, I think Hawking's original calculation is extraordinary. It's very beautiful. It has the potential to give us really revolutionary insight into new physics. My complaint is that what has come after this explosion of different ways of deriving the Hawking radiation and the Hawking effect, they all mostly agree that yes, very, very, asymptotically far away, we get the Planckian spectrum, the Planck, and the temperature encoded is proportional to the surface gravity of the event horizon, with the proper coefficient. And that's great. They all agree on that. That's fantastic. And that does very strongly suggest that insofar, if any of these ideas are on the right track, then that conclusion certainly is on the right track.
Oh, okay, so you agree with that? Because it sounded like you did. It sounded that you were questioning that.
I agree with that. What I worry about is that all the different derivations suggest very different physical interpretations for the mechanism that produces the radiation asymptotically far away. And I think that's what we very much need to understand that. I don't know how to give a consistent kind of unified physical picture that covers the tunneling derivations, the S-matrix derivations, and the algebraic derivations. I don't think there is one. So I would very much want to know what the kind of physical picture, physical mechanism of the Hawking effect is. That was my point. On the second issue, I completely agree that unfortunately my discussion of the page curve and the issues that you're exactly talking about are in the part of the talk that I didn't get to. So I will show one slide that says what I want to say here. So can you all see this slide with particular regard to the page curve problem? Someone? Anyone?
Yes, we can.
Okay, thank you. So, so I think I think one way to perhaps even to sharpen what you were saying about the assumption that goes, the further assumption that goes into the page curve problem is that the argument assumes that we can model a black hole as an ordinary, quantum mechanical system to which we can apply quantum statistical mechanics. And so whatever micro degrees of freedom there are that we're applying the statistical mechanical treatment to, in order to get the problem off the ground, you have to assume that those micro degrees of freedom can be entangled with the degrees of freedom in the Hawking radiation. Hawking radiation is a macroscopic phenomenon, relative to fundamental quantum gravity. It's just ordinary quantum fields. It's photons. The black hole micro degrees of freedom presumably are something like low perturbative low energy quantum gravity degrees of freedom, whatever exactly that may come to. And I actually have a very hard time seeing how it is that these perturbative low energy quantum gravity degrees of freedom are supposed to couple in the right way with degrees of freedom of ordinary matter at really, really low energy and gravity scales. At energy and gravity scales that should be easily accessible at the LHC, if you're thinking about very big black holes. And there's a further step that has to be made that no one ever seems to mention in the page curve problem when they're talking about this stuff. It can't just be that there are micro degrees of freedom, low energy perturbative quantum gravity degrees of freedom in the black hole that couple in the right way with the entangled with Hawking radiation. They actually have to. What actually has to be the case is there has to be the right degrees of freedom in the black hole. In particular, it has to be degrees of freedom that give rise to the affine structure. When these perturbative quantum degrees of freedom, give rise to classical space-time geometry. If they aren't the degrees of freedom that give rise to the affine structure, you're not going to get the right behavior for the Hawking radiation, because Hawking radiation is guided by the affine structure of the space-time. So my problem with the page curve problem, with the way that it's set up and the assumptions that go into it, and the reason why people seem to freak out, I actually think that there are several very dubious and questionable assumptions that go into it. I know you have some other problems that have to do with the entropy, which I also am very sympathetic with. So yeah, I wanted to talk about that, but they're later in the slides. So if you're interested, but that's essentially what I have to say.
Okay, thank you. Now that makes that much more.
Yeah.
If there are no other questions, I have another one, but I would like other to speak if they want. I don't want to monopolize the conversation.
There are some in the chat, but we're over time.
We had 2 questions in the chat. Yes.
Yeah, I'm not sure. Should I go on, even though I think we're over time?
Yeah, I think it's okay. Well, people can leave. I think if they have to. Yeah.
I will not be insulted. I'm happy to go on a little longer. So a question on the slide on the chat: what would be the fundamental problem in incorporating the back reaction of fields on space-time? Could this back reaction help us better understand space-time at the quantum level? So the problem in incorporating back reaction is just that the main one, as several people here, Don and others can say even more authoritatively than I can, it's really a technical problem. The semi-classical Einstein field equation, which is the only way we know right now to explicitly try to incorporate back reaction, is just monstrously difficult to solve even under the simplest and most in the simplest spacetimes with the most extreme idealizations. We know very, very few exact solutions for it, and we really don't know how to use it as a guide for dynamical evolution. So the problems, as far as I'm concerned, the most important problems right now are technical. There are some important conceptual, I think, problems with it, but until we can get the technical material under control, I don't think we should be worrying about the conceptual problems. I don't think it would actually help us understand space-time at the quantum level, because again, it would still be formulated on a classical space-time background. So maybe I'm too pessimistic about that. Maybe in fact we would, if we could get back reaction under control, we could draw some lessons about space-time at the quantum level, but it doesn't seem promising to me. So the next question from Stephen Fulling: your point of view seems to me to be essentially the same as Unruh and Wald. It is, in some ways. Why do you say you disagree? If you're talking about what I said in the abstract, where I said my reasons are somewhat different from Bob and Bill's.
Yes.
Yeah. My reasons, I think I do share many of the same reasons, and just for the purposes of complete disclosure and honesty, Bob was one of my advisors in physics, and I was trained as a classical relativist. No surprise that I shared many of their predilections and prejudices, although I fight against it. The things I think in which my reasons are somewhat different. So some of their reasons I completely endorse and agree with, and I think some of the things I said, as you rightly point out, are exactly in line with what Bill and Bob say. What I think I tend to focus on that they don't is what I call the temperature decoupling problem. That to me is a very serious worry. And I've talked to both Bill and Bob about it, and they say, yeah, Eric, what you're saying is totally right, but we're just not worried about it because, well, they don't worry about it because they already think that we shouldn't be worried about unitarity violation, and they think that the semi-classical framework is just so manifestly and obviously an effective framework that we shouldn't be worrying about any kind of deep conceptual problems associated with it. So my further concern in what I call the decoupling problem is something that they at least in my conversations with them, agree is a problem, but they think that they can dismiss the worries about unitarity even earlier than that, so they're not worried about it.
Thank you.
So,
Elaine?
so if there are no other questions, are there any last questions?
If I can continue with if there's nobody else, I can continue with may I? Eric?
Yes, please.
If one, since you got to the page argument,
Mhm.
again, if one looks at page derivation, the reason it might be wrong, it seems to me, is not because somehow the physics beyond the approximation of the given by quantum field theory on curved space-time might be out of control. It seems to me the opposite. If the physics of quantum field theory on curved space-time in that regime, the page regime, is correct, then there is no page argument. That's the point. I mean, it seems less mysterious, the situation to me. Page argument relies on an idea, which is that quantum field theory on curved space-time goes wrong. And the reason it goes wrong is because of the assumption that the number of degrees of freedom is given by the inside the black hole is given by the Bekenstein-Hawking entropy. So it's not that we don't know the physics beyond that approximation, and therefore we're confused. Is that because Page thought he knew the physics beyond that approximation? In other words, you say, what are the degrees of freedom that purify the Hawking radiation? Well, just take standard quantum field theory on curved space-time. They are not gravitational degrees of freedom. They're just a part of the Hawking radiation, which is fell in. I mean, from two-dimensional models, we know that all the radiation goes outside and inside, and the two are correlated. The two are correlated and perfectly account for the non-purity of the outside. So there's no mystery. But Page says, okay, but let's bring in the extra idea that the number of degrees of freedom of black hole is limited by the area. I think it's just confusing the thermodynamical entropy with the von Neumann entropy of the entanglement. And of course, this is taken seriously by a full community which want to think holographically and think that there is everything can be accessed from the outside. A black hole is not, you said, treating it as a general statistical system. Even if you treat it as a general statistical system, it's certainly not an ergodic system, because what the information goes in doesn't come out. So it's not true that the von Neumann entropy is bounded by the thermodynamical entropy. So it seemed to me the confusion comes, the black hole information paradox comes not from quantum field theory first curved space-time, not on its limitation, but on the assumption that comes from believing in holography and believing in a certain interpretation of the Bekenstein-Hawking entropy, namely that it counts degrees of freedom.
So I personally find what you say very convincing and very compelling, and I'm actually very curious to know what people like Don say in response, but he's not here, so
I would like to know what their response.
But I also just can't help pointing out a really delicious irony here. So one of my favorite papers in all of physics is this paper from the 90s that you and Don and Ted Jacobson co-wrote, this three-way dialogue called something like
the trialogue of
where does black hole entropy live, or something like that. And in which, in that paper, you defend the idea that all the relevant degrees of freedom live on the horizon. Don defends the idea that all the degrees of freedom live inside, and Ted is kind of agnostic and just not sure which way to go. And today, 30 years later, it's exactly the opposite, or at least there's
No, it's not the
at
opposite.
least there's a parity reversal around Ted. Ted is still agnostic, and you think all the degrees of freedom live inside, and Don thinks all the degrees.
No, not at all, not at all. I'm not saying that the number of degrees of freedom that have to do with Hawking radiation live inside. Not at all. I'm saying that the degrees of freedom that are inside, period. They have nothing to do with Hawking radiation.
Okay.
For sure, because the Hawking radiation outside, how can it know about it? But it gets entangled with it. So if you cut the inside, throw it away, you still have production of Hawking radiation, but of course you lose information.
Well, that I think seems to me at least like a good place to stop. Eleni, Don, Paolo, Benito.
Yeah, I think that's a good place to stop. But thank you for the conversation. So before we say goodbye, our next talk is on the 31st of March.